Alrighty, today we are talking about recursive searching. So the linear, very, very simple. We have an array, we have the value we're looking for, and then we're just going to loop starting at 0, going up until the length of the array. If the thing we're looking at is what we're looking for, return the index. Very, very simple. Not a whole lot to it. Now, today, we're going to be learning about another searching algorithm called binary search. Binary search is much, much more efficient than linear search. However, it has one precondition. The array needs to be sorted in order for binary search to work correctly. So the way that binary search works is it finds the midpoint of an array. It checks if the value at that index is greater than, less than, or equal to what we're looking for. Depending on the result, we can eliminate half of the array from the search each time we perform a check. So let's look at how this looks and we'll work it out. So during the execution of binary search, there's a few different values we're going to keep track of. Value number 1, what we're looking for. Value number 2, the index at the beginning of where we're searching. And value number 3, the index at the end of where we're searching. So let's say we want to find the number 3 in this here array. We are going to want to start first by looking at the entire array. So the value we're looking for is the number 3. Our beginning index is 0. Our ending index is 8. It's the final element in our array. So we can find the midpoint by finding the average of the beginning and ending values. So we're going to add 0 plus 8. We're going to divide that by 2, and that gives us 4. Now, we want this to be an integer division so that we have a whole number. We don't have half of an index. So even if our sum on top of the division comes out odd, we don't want to have half of an index. That's not how arrays work. We can't have array index 4.5. So even if we do have an odd value, we're going to divide by 2 and truncate so that we get an integer value. So our mid value is 4. Then we're going to compare our value at our midpoint index to the thing we are searching for. Is 3 equal to 8? No, those two values are not the same. So then we're going to compare whether the value we're searching for, 3, is greater than or less than the value at that index. 3 is less than 8. So now we know, since this array is in order, everything at and to the right of that middle index, 3 can't be found in there. 3 is absolutely, definitely not in that area. So we can eliminate all of those values from our search. So we can move that ending to 1 in front of the middle value, because we know index 4 and beyond definitely does not contain the number we're looking for. So we're going to move that ending to equal mid minus 1. So ending is going to move to 3, and everything beyond index 3 has been eliminated, because we know for a fact none of those elements are going to equal what we're looking for. And then we're going to repeat this process until either A, we find what we're looking for, or B, the beginning and ending pass each other. If they have gone past one another, we know that the value can't be found. So let's keep going. the average of 0 and 3 is going to give us 0 plus 3 is 3. 3 divided by 2 is 1.5. We truncate down to 1. So our middle is now 1. 3 is greater than 2. So we're going to move our beginning this time. We're going to move our beginning past because we know that it's not less than, or we know that it can't be to the left or equal to this value. So we're going to move our beginning and exclude both of those values from our search. Now our beginning is 2, our ending is 3. 2 plus 3 is 5. 5 divided by 2, when we truncate, is equal to 2. So now our mid and beginning are both looking at index 2, and that's totally fine. We can have multiple of these things looking at the same exact index. Now, is 3 at this index equal to the 3 that we're looking for? Yes, those values are now the same. So we know that this is the correct index that we've been looking for. We can return index 2 because that is where we found this value. Now let's imagine that instead of searching for the number 3, we were searching for the number 5. So we get to the same exact spot, but we see that 3 is less than 5. So the number we're looking for is bigger than what we see here. So we're going to move our beginning up again. So now beginning and ending are looking at the same exact spot, but they haven't passed each other. So it's possible that it could be at this index. So we're going to find the midpoint. We're going to average 3 and 3. Obviously, the average of the exact same number is going to be itself. So we're going to look at index 3. Beginning, middle, and ending are all looking at index 3. Is 5 equal to 6? It's not. 5 is less than 6. So we are going to move our ending because we know it's not going to be anywhere to the right. So we're going to move the ending to the left. And now we can see ending is lower than beginning. So we've eliminated every single index from our search. We know none of these indices are capable of holding that number 5. Therefore, we know 5 isn't present in our array. We can return -1. So, some comparisons between linear and binary search. Linear search is not very efficient, but it works on any array, whether it's sorted or unsorted. And linear search is very, very easy to code. You're just looking through every single element, checking if it's what we're looking for. Binary search, however, is incredibly efficient, but it only works on sorted arrays, and it's a bit more complex to program. So if we want to kind of calculate the efficiency of this linear search algorithm, we know that in the very worst case for a linear search, we're going to have to check every single element. And as the size of our problem increases, so does the number of checks we have to make. If I have a list with 10 elements and the number I'm looking for is at the very end, I need to check 10 times if what I'm looking at is my current value. And as I add more elements, I have to check more and more times. With binary search, anytime we perform one of our checks, we can eliminate half of the remaining elements in the sequence. And what this means is that we have to do way, way less comparisons to eliminate every available index. So since we're dividing the number of elements to search through in half, we're dividing by 2 every time we do a check, we can use an exponent to determine the maximum number of elements that we can search through given a specific number of checks. So if I have X checks, I can search through an array with up to 2 to the X elements in it. So if I have 3 checks, I want to check 3 times, I can have an array with up to 2 to the 3 elements. It can have up to 8 elements in that array. If I want 4 checks, I can have 16 elements. We're doubling the number of elements each time we add a number of checks. And we can kind of invert this value with a logarithm. If we know how many elements we have, we can determine the maximum required number of checks. If I have an array of length n, the most checks I will possibly need to find whether a value is present is log base 2 of n number of checks. So that is our absolute worst case, log base 2 of n. Now, that is so much more efficient than our linear n number of checks with linear search. Every time I add a new element, I need to check exactly that many times with linear search. Where here, anytime we add an element, it's only going to add potentially a fraction of a check each time. So we can check much, much larger arrays in a much faster time using binary search. So if I have an array with 512 elements, what is the maximum number of iterations that would be required to find any given item? Log base 2 of 512. The answer is 9. I couldn't remember how logarithms worked for a long time. So it's okay if you don't remember how logarithms work off the top of your head either.
I haven't memorized like exponential.
You know, I haven't either. It's been a long time since I had to think about logarithms. So if I have 512 elements in my array, the most number of checks I need to do is 9. And that's crazy. If I were using linear search, I would need, or the maximum number of checks I would need to do is 512. So that's an order of magnitude lower. So binary search, much, much more efficient than linear search. So if we want to actually write binary search, we can do it using either loops or with recursion. Either way, both work. So let's first look at how we might implement it using a loop. So our binary search method, we're going to get our list of numbers, and we're going to get the value we are searching for. We're going to initialize our beginning and our end. Begin starts at 0. Our end starts at the end of the array, as you might expect. And we're going to loop as long as our beginning value is less than or equal to our ending value. We're going to calculate our mid value. It's going to equal begin plus end divided by 2. Or not if, we're going to find that midpoint, and then we're going to compare that midpoint, or the value at that midpoint, to the thing we're searching for. If our value is less than the number at our midpoint, we're going to move our end to eliminate the upper half of the array. If our value is bigger than the number at the midpoint, we're going to move our beginning and eliminate the lower half of the array. And if we've found what we're looking for, we're going to return that index. If we make it all the way through this loop without having found our value, we're going to return -1. So let's run through an example. I've got my nums array equaling 4, 12, 18, 27, 34, 44, 51, 63, 67, 74, 91. We are searching for the number 51. So in my first iteration, my begin starts at 0, my end starts at 11. 11 divided by 2 is going to equal 5. So my midpoint is 5. So my nums at mid equals 44. 44 is less than 51. Our value is too big. We're going to move our beginning because we know that our value is not going to be anywhere to the left of our midpoint. So we're going to move our beginning to be one past that midpoint. So now our beginning is at 6, end is still at 11. We haven't moved it. 11 plus 6 is 17. 17 divided by 2 gives us 8 once we truncate. So our midpoint is at 8. The nums at position 8 is equal to 67. 67 is bigger than what we're looking for. So we are going to move our end because we know that nothing at or to the right of our midpoint is going to contain what we're looking for. So we're going to move our end to be 1 less than mid. We're going to move 8 to be equal to 7. Begin at 6, end to 7. Mid is 13 over 2. That equals 6 once we truncate. So our nums at mid is equal to 51. And hey, we found our value. We can return the index where we found it. We found it at index 6. That process makes sense? All right. Now, we can implement this same exact method using recursion instead of loops, because just about any time we use a loop, we can usually implement that same thing with recursion. So we can do binary search with recursion. There's going to be a few extra parameters we pass to our method. We're still going to get our array of numbers. We're still going to get the value we're looking for, but we're also going to get the indices where we're starting and ending. We have our base case, our way to stop our looping, stop our iteration, and it's the same as in our while loop. If our beginning has passed our end, we're going to return -1. Say, hey, it can't be found. It's not in here. We're going to calculate our midpoint. Once again, it's the exact same calculation, begin plus end over 2. And we have that same sequence of if statements. If our value is less than the midpoint, if our value is greater than the midpoint, or if it's neither of those things, it has to be equal. So then we will return the index we found. So if the value is less than the index we were looking at, we're going to move our endpoint. So we're going to call binary search again. We're going to move, we're going to pass those same values, nums, value, and begin are all the same. We don't want to move the beginning, but we do want to move the end. So end is going to be changed. We're going to say mid -1 for our endpoint the next time we call binary search. And we're just going to return whatever that returns. So the same is true with our value greater than none. We're going to move our beginning. The end is going to stay the same. And we're going to return whatever that method returns. So let's say we have the same exact array of numbers, and now we're looking for the number 4. So the first time we call our method, begin is going to be 0, end is going to be 11, just like last time. So those are the values we would pass the first time we call our method. And our midpoint still is equal to 5. So our nums at that midpoint is equal to 44. 44 is still greater than the number we're looking for. So we're going to call binary search. We're going to move our endpoint. We're going to call with the endpoint equaling mid -1. So we're going to call binary search with 0 and 4 as the parameters. Beginning is still 0, mid or end is now 4. We're in our second call. Someone asked a question, or did you just hear something? I think I just heard something. Never mind. 4 over 2 is 2. That's our midpoint. Array at our midpoint is 18. Still greater, so we're going to call the same method again. We're going to call binary search. We're going to move end once more. End is now 1. 1 divided by 2 is equal to 0 once we truncate. And then the value at index 0 is 4. 4 is what we're looking for. So we're going to return that index. We return 0. And then when we get back to the previous method where we called before words, so where we called our method where we found the value we're looking for, we return 0. So we're going to return whatever that one returned. And the same is true. We're going to return whatever that one returned. Eventually returning 0 from the first place we called our binary search method. So why would I choose one of these over the other? Why would I choose recursive or iterative with a loop for binary search? Now, fortunately, with the binary search algorithm, either approach offers about the same level of efficiency from a speed and memory perspective. So choosing one over the other is generally just going to be personal preference. So whichever one you feel suits your needs better, use that one. So we learned 2 different searching algorithms in this class, and they're both going to be kind of at least a little bit covered on the AP exam, to my knowledge. Covered linear search and binary search. Linear search is way more efficient than linear is much less efficient than binary search, but binary search requires that the collection is sorted before we do our searching. Now, something to keep in mind is if our total efficiency of a search and a sort, or a sort and then a search, is less than a linear search, it might be worth it unless we care about the original list sequence, in which case we might not want to actually sort it and then find something. But if we don't care about the original sequence, if we're just checking if something is present, sorting and then searching might be the best solution in an efficiency perspective. And the binary search algorithm that we learned about today can be written either recursively or with a loop, whichever one you feel best suits your needs. So that binary search algorithm starts in the middle of a sorted collection. It's going to eliminate half the values each iteration until we have found what we're looking for, or we've eliminated all elements. Any questions on binary search?